In the previous video we were looking at periodic motion. We're now going to focus on a specific type of periodic motion, being simple harmonic motion. Now, in order to describe simple harmonic motion, there's a set of circumstances that we can refer to do with the force and the acceleration. I'm going to refer to the acceleration rather than the force. So the first thing is that the acceleration, and you could then also say that the force, given that we know that force is equal to mass times acceleration, that acceleration is proportional to the displacement of the object. And so that means that if the displacement gets larger, then the acceleration likewise gets larger, and that also means if the displacement gets larger, the force gets larger as well. The second thing is that the direction of the acceleration is always in the opposite direction to the displacement. And again, the direction of the force would also be opposite to the direction of the displacement as well, given that force and acceleration are in the same direction. So that's always opposite the displacement. That means that we can express that in a proportional relationship, and that proportional relationship would be that the acceleration A is proportional to negative x. Now, if we were to graph that relationship, pretty straightforward. As we see the displacement x increasing, so we'll graph x on the horizontal axis and a on the vertical axis. As the displacement increases in the positive direction, the acceleration is going to increase in magnitude, but it'll be negative, and so we'll see this line coming down this way at a constant gradient. And then as the displacement goes in the opposite direction, then the acceleration will likewise be in the opposite direction to that, and so we get that linear trend line. Now the values on the horizontal axis here, that would be x naught, so the maximum displacement, and then negative x naught, and likewise on this axis that would be a naught and negative a naught, so the maximum is in those directions. Now, to take this a little bit further, we're going to have a look at a particular scenario. So we're going to have a look at a pendulum, and to start with I'm going to draw the pendulum as being positioned out here somewhere, and then we'll indicate that there's the equilibrium position here, and initially we're interested in the displacement of the pendulum, so we're looking at this value here being the displacement x. We know then also that the acceleration is going to be in the opposite direction to that and proportional to it. I'm just going to represent this as about half as big as the displacement, but how big it is would depend on, say, the length of the pendulum itself. We also know out here that the velocity of the pendulum is going to be 0, so it's going to be stationary for that brief instant while it's swinging out there. If we consider what happens when the pendulum is swinging through the equilibrium position, we know there that the displacement is going to be equal to 0, so we can jot down displacement is equal to 0. And likewise, because the acceleration is proportional to the displacement, the acceleration will also be 0. Now the velocity here is going to be at its maximum, so as it swings through that point we're going to see the velocity being greater than it was, or greater than 0. If we consider somewhere sort of partway in between, so if we look at a region here somewhere, so as the string's moving in that direction, you can see that the displacement is a bit smaller, which means likewise that the acceleration is going to be smaller at that particular point there as well, but still in proportion to the displacement, and the velocity is going to have increased from 0, but it won't quite be as big as it was in the equilibrium position. Now if we continue on to the other side, so same sort of situation, if we look at the as it starts to swing out in that orientation, we've now got the displacement going in the opposite direction, which means that the acceleration is now going to be coming back towards the equilibrium position there, and the velocity likewise will still be to the right, but not quite as big as it was through the equilibrium position. Finally, on the right hand side, so if we have the object now positioned all the way out to its maximum on the right hand side, we're back to that situation again where the velocity is equal to 0. The displacement will be out to the right, and the acceleration will be back towards the middle. I know there's a lot of messy notations there. Just wanted to really clarify those points first, so that we can then take this to a graph. So if we consider the graph that we're dealing with here, I'll try and make sure that the graphs line up with those positions. So looking at graphs of displacement time, velocity time, and acceleration time. So looking at those three graphs, we're going to use that this diagram to at least start off looking at what's happening in each scenario, to then make sense of how these graphs are linked together. So first of all, we have displacement versus time. So time on the horizontal axis and displacement on the vertical axis. We can see in this initial position here, so when t is equal to 0, we're at this point here, which is the maximum displacement x0. Now, when we go across to the equilibrium position, we can see that the displacement there is 0, and then likewise when we go to the other side, the displacement is a maximum but in the opposite direction. So important to note here that the direction to the left is positive and to the right is negative. So that's how we've represented it on the graph below. We can also see there that partway through the displacement has decreased, and likewise as it continues to move the other way, the displacement starts to increase in the direction to the right. So there's the displacement versus time graph, and we can see that that continues in a periodic manner. If we then go to the velocity versus time, so I'll just mention it here first. Initially we're going to start out with the velocity being 0. The velocity then increases to a maximum and then decreases back to 0. Notice that the direction of the velocity doesn't really match up with the either the displacement or the acceleration. So on the left hand side, the velocity is opposite to the displacement and in the same direction as the acceleration. On the right hand side, the velocity is in the same direction as the displacement in the opposite direction to the acceleration. Now when it starts to swing back to the other side, so back towards the left, the velocity will then change direction, and so that will then be the opposite. But if we go down and have a look at the velocity versus time graph, again on the horizontal axis we have time, but now we've got velocity on the vertical. So we can see initially the velocity starts off at 0, then increases to a maximum as the object is passing through the equilibrium position. Once it then reaches the other side, then the velocity has once again decreased to 0. Notice that we started off with a cos function for the displacement, and we've now got a sine function for velocity. Going on then to the acceleration versus time, we can see we once again have time on the horizontal axis and now acceleration on the vertical axis. And we can see that the acceleration is initially directed to the right, as we saw in the diagram above, so in this diagram here, and then decreases to 0 when the object passes through the equilibrium position, and then increases to a maximum directed to the left, and then continues on as we look at that the rest of that oscillation. Now if we just have a look at all three of these graphs on the screen at once, hopefully what you can identify there is that we have the acceleration and the displacement, so the top graph and the bottom graph, they're doing the same thing but in opposite direction. So we start out with the acceleration as a maximum to the right, and the displacement is a maximum to the left. Then they both decrease to 0 at the same time, and then increase to a maximum in the opposite direction at the same time, and then continue on with that same sort of doing the same thing at the same time. Now the velocity, you'll notice, is a little bit out of sync to that. It doesn't quite match that same pattern, and we'll have a look at how we can describe that, what the term is that we use for that situation. Now in that situation, while all three graphs have the same period, it makes sense considering that they're all part of the same scenario, they are doing different things at different times in terms of maximums and minimums. so they don't all have the same starting point, for one thing. So they don't all start at a maximum, and they don't cross the axis at the same time either. So they don't have zeros at the same time. And what we would then say is that they have a phase difference. So that's the term that we use to describe the fact that they have the same period but are not doing the same thing at the same time. So phase difference is the term that we'll use there. Sometimes you might hear it as phase shift. Now, if two oscillations are in sync, doing the same thing at the same time, they would be said to have no phase difference. So two oscillations that are in phase. So by in phase we mean they're doing the same thing at the same time. They have zero phase difference. If we have them that are doing exactly the opposite thing, so one's at a maximum while the other's at a maximum in the opposite direction, so we'd say that they are out of phase. They have a phase difference of either, if we measure it in degrees, we'd say that it's 180 degrees, or if we use radians, it would be pi radians. So either of those two. So be aware of both. You might need to refer to both at different times. The way to think of that is to consider a sine function. So if we had a sine function that looked like this, and then we had another one that was out of phase, it would look something like this. Amplitudes don't necessarily need to be the same, it's just about the time taken. So in that scenario, imagine if you think about the sine function, this point over here corresponds to an angle of 2 pi, and this would correspond to an angle of pi. Now if we take that green line and shift it entirely pi radians to the right, then we'd see that it would actually end up being then in phase with the orange diagram there. So the phase difference means that it's out of phase by 180 degrees, and so doing opposite things at the same time. We can then have any other sort of scenario as well. If they're so thinking now about the displacement and the velocity, if we have a phase difference of 90 degrees, so two oscillations could be different by, say, 90 degrees, and that basically would then be pi on 2 radians, so either of those two. What that means is that we have a similar situation again. If we start out with the this sine wave looking something like that, to have a phase difference of 90 degrees, it basically means that if this is where the starting point is for the first graph, 90 degrees or pi on 2 radians later would be this point here. So imagine now we're sort of shifting that across, so that instead of the 0 being at the beginning, the 0 is now going to be here, and then this point would likewise shift pi on 2 radians across to be here, and you can see there that if we continue that pattern, we're basically going to end up with a negative cos graph in this scenario. So pi on 2 radians, or 90 degrees phase difference, means that we have one passing through the equilibrium position while the other is at a maximum, and then when that second one is passing through the equilibrium position and the first one is at a maximum. So that would be a phase difference of 90 degrees or pi on 2 radians. We're only really going to deal with those three, so 0, 180 degrees and 90 degrees, but we could have any angle in there, 45 or 30 or 27 or anything at all. But for the purposes of what we're looking at, so getting back to this idea for simple harmonic motion, we have some phase differences that we can talk about. So for simple harmonic motion, we would say that the velocity and displacement, so v and x, have a 90 degree or pi on 2 phase difference, given that, as we saw before, that velocity is 0 when displacement is at a maximum, and the other one that we're interested in is the acceleration and the displacement, and they have a 180 degree or pi radian phase difference. To make sense of that, you might want to go back and have a look at the graphs all on the one screen and identify the phase differences that are involved there. So we'll have a bit more of a look at some problems in class. There are a few multiple choice questions I can think of from past papers that are really useful ones to look at here. Being able to identify what a velocity time graph might look like given the displacement time, or relating, say, the acceleration versus time and the displacement versus time. So we'll look at a few of those sorts of things in class.